Hello and welcome back to Pyman Tutoring. This video is part 2 of the series on graphing functions using the first and second derivatives. In the first video we went over the principles. Now we're going to go through a series of examples to solidify your understanding. Let's begin. So here we go, example 1. We've got f of x is 1/2 x to the 4th minus 16 over 3x cubed plus 16x squared. So going through our simple flowchart, first of all looking for discontinuities. This is a simple polynomial. And therefore there are no discontinuities. There are also, because it's a simple polynomial, no vertical asymptotes, no horizontal asymptotes. So that's nice. Intercepts. Well, let's find when f of x is equal to 0. We can pull a common factor out of f of x. X squared comes out. Actually, x squared over 6 comes out. And that leaves us with 3x squared minus 32x plus 96 inside the bracket. So we can say that this is equal to 0 if x equals 0. Actually, it's a double root because of the square at that location. And if you try to find factors of everything inside the bracket, you will not find any. You can do the discriminant check to prove that. So b squared minus 4ac would be 32 squared minus 4 times 3 times 96. And that gives us negative 92. So clearly there are no additional roots. So we know that when x is 0, f of x is 0. So basically the function passes through the origin. Now we move on to our new stuff, f dashed of x. We do the derivative of that. We will get 2x cubed minus 16x squared plus 32x. Looks like we can pull out a factor of 2x from that. And that leaves us with x squared minus 8x plus 16 in the bracket, and that looks like it will factor. Product is 16. Sum is 8, so that looks like 4s to me. So 2x into x minus 4 squared. So for critical values, we want f dashed of x equal to 0 or does not exist. Well, clearly in this expression there are no limitations on the domain. So what we're left with is x equal to 0 or x x equal to 4, and that's also a double root because of the squaring. And we can do the second derivative, which would be first function times the derivative of the second plus the second function times the derivative of the first. Now we can pull out the x minus 4 factor, it's a common factor. There's also a common factor of 2 in there, and we're left with 2 lots of x plus x minus 4, which is 2 into x minus 4 into 3x minus 4. And this has zeros if x equals 4 or x equals 4 over 3. So now we're in a position to make our strip table. Let's do that. So f of x, f dashed of x, f double dashed of x. And what have we got for values? Well, we've got 0 at 0 for the function. We've got critical values at 0 and 4 for the derivative. And we've got 4 and 4/3 for the second derivative. So everything is positive. So let's start with 0 here. We have a 0 in the function at 0. We have a 0 in the derivative at 0. And that's it for 0. The next point we have is 4/3. That only gets a mention as a 0 in the second derivative. And then we have the point x equals 4. And that is a double 0 in the derivative. So let's now use the table to help us plot this particular function. We know that we have a point 0, 0 on the graph. What do we know about f dashed of x? Well, if we go over here to the left of 0, if we put a negative number into f dashed of x over here, a negative number will produce a negative slope. So we know that we have negative slope to the left of 0. If we put in a test value of 1, positive 1, we know that we will get a positive value. And so here we have the conditions for a minimum. We have a negative slope going to a positive slope at 0. As we move above 4, if we put in a value of 5, say, we end up with a positive value again. So we're going to get a 0 slope at 4, but then we're going to continue with a positive slope. And let's say this is 4 just here, so positive slope up to 4, where we have 0 slope, and then we take off again in the positive direction. And then at 4 over 3, just here, we have a 0 in the second derivative, which might indicate an inflection point. Actually, I missed one of the zeros for the second derivative. Just put that in at 4. So we've got two potential places where we might have inflections going on. Second derivative is 0. The question is the curvature changing from positive to negative or negative to positive as required for an inflection? So the second derivative, if we feed in a value of 0 into the equation, we will get two lots of 0 minus 4, that's a negative 8, multiplied by negative 4, so we end up with a positive curvature. And that's consistent with the requirements for a minimum. As we move past 4/3, so let's assume we have a value of 2, and we feed that into the second derivative, we will get 2 times 2 minus 4 is negative 4, multiplied by 6 minus 4, which is positive, and so indeed the curvature on this side has now gone in a negative fashion. So we came out of here with concavity upwards, and at 4/3 the concavity is now downwards as this curve is turning the corner, and then at 4 we can see that the curve is heading up again, so we might expect this to be positive. Let's put in a value of 6. Both of the brackets become positive, so indeed the second derivative is positive, which means we now are back to concavity in this fashion. And so sure enough, we do have genuine inflection points at 4/3 and at x equals 4. We can just quickly look at the end behavior. As x tends to infinity, f of x would tend to positive infinity, and as x tends to negative infinity, because of the even power on the x to the 4, we would expect this function to head off to infinity as well. So that's it. We've done the analysis, and this is the graph of this function. Let's do another. Okay, here we go with example number 2. Let's say we have our f of x is equal to 3x minus 6, all raised to the power of 2/3. Alright, step 1. Are there any discontinuities in this function? So there are no values of x that produce any vertical asymptotes or horizontal asymptotes, so looks like we're okay there. What about zeros? Oh, intercepts, I should say. So first of all, we set x equal to 0, and we find the value of f of x, and that would be equal to minus 6 to the power of 2/3. And what does that mean? That means square the minus 6, which gives me 36, and take the cube root. Similarly, if we want to find the x-intercept, we need to set the y value equal to 0. So that's where f of x is equal to 0. And for that we need 3x minus 6 to be equal to 0, which implies that x is equal to 2. So we have one intercept at x equals 2, and the other is where f of x is equal to the cube root of 36. Okay, now we move on to the first derivative. So f dashed of x. So here we use the chain rule. We bring down the 2/3 multiplied by the original function, drop the power by 1, which means negative 1/3, and then multiply by the derivative of the inside function. So that'll give me a 3. Now this 3 and this 3 cancel out. So what I'm left with is 2 divided by 3x minus 6 to the power of 1/3. So notice that I've moved this term into the denominator of the fraction. The reason for doing that is it's easier to spot when the function is undefined if you put it as the denominator. So as we move it to the bottom of the fraction, we change the exponent from minus 1/3 to positive 1/3. And now it's quite obvious that this derivative does not exist if x is equal to 2. So that is our critical point for the derivative. We also look for zeros of that derivative, but there's no way in which we can make this derivative function equal to 0. So the only critical point we have is x equals 2. Alright, now we can move on to the second derivative. And that is equal to, again we use the chain rule, so looking at this expression above, we'll keep the 2. We bring down the power, which is the negative 1/3, so that will become negative 2/3 multiplied by the inside function. We reduce the power by 1. So minus 1/3 minus 3/3 gives me minus 4/3. And of course we have to multiply by the derivative of the inside function again, which is another 3. So what can we do now? Once again the 3's cancel nicely. So we're left with negative 2, again we'll write it as a fraction, over 3x minus 6 to the positive 4/3. And now critical values, again this does not exist if x is equal to 2. And once again we cannot get this second derivative function to be equal to 0, so we just have the one critical point in this case. Just one more thing to notice is that this critical point here is a single because we have a power of 1 in this exponent. But for the second derivative, we have a power of 4 in the exponent, and so this will be a quadruple event on the graph. Okay, so we've done all of that, and really we've only found a single critical point in all of this. So let's now make our table and see what that all means. So here's my table. The first strip will be the function itself, second strip is the first derivative, and the third strip is the second derivative. Now we grab our critical point, so at x equals 2, what do we have? In the function itself, we know that at x equals 2, we actually have a 0. So we mark that with a solid line. When x equals 2 in the first derivative, we have a does not exist. So we mark that with a single dotted line. And in the second derivative, we said x equals 2 does not exist, and it's a quadruple event at that location. So we've put all of our critical points on the chart. Now what does it all mean in terms of slopes and increasing, decreasing functions? Well, taking the first derivative first of all, we can look at the first derivative expression, this equation up here, and we can say what happens if I choose a value below 2. A convenient value to choose is 0, and so we would have 2 divided by minus 6 to the power of 1/3. So we're going to end up with a negative value in here. If x is greater than 2, then the denominator in that expression will be positive, and so our first derivative is positive on this side of 2. So we've got a slope going down, followed by a slope going up. Now let's look at the second derivative. Just change the color here. Let's go with orange. So this is my second derivative expression. If x is below 2, what happens? Well, 3x minus 6 would be a negative number, but it's raised to the power of 4, so that turns it into a positive number. But we have a negative 2 on top, and that means we'll be left with a negative value on the left-hand side of 2 in this case. Now what happens on the right-hand side? When x is greater than 2, the denominator is again positive, so the minus 2 on top again defines the sign of the second derivative. So we've got a negative curvature on both sides of the number 2. And remember, a negative curvature means this kind of shape. The slope is getting more negative. And so in both cases we're saying it has this kind of shape. And when we combine those two pieces of information, we want something going down and with negative curvature. So that combination gives me this overall shape. Over here, this combination going up and having that kind of curvature means I need to have this kind of shape on the other side of 2. We can also quickly look at the first strip in the table. What is the value of the function, positive or negative, when x is less than 2? So it doesn't matter what I have inside this bracket. At the end I'm going to square it before I take the cube root, and therefore regardless of the value of x, this function will always be positive. So let's look at our graph now. We've got a critical point at 2. We've got a function that's positive. We know from this point up here that it crosses the axis at the cube root of 6. We know from this left-hand side of the table that we need this kind of shape coming into the point 2. And from this side on the table we need this shape going out. And so this is what we call a cusp. And we can just check the end behavior of this function to make sure that we've got everything right. So as x gets bigger and bigger, the function will grow to infinity, so that makes sense. And as x goes into negative territory, we said that we are squaring the inside function, and so this will continue to positive infinity as well. So everything looks good. That looks like the correct plot for this particular function. Let's do another. Okay, example 3. F of x is the cube root of, let's make that clearer, is the cube root of x minus 6, which we know we can write in exponential form. So discontinuities, no. Vertical asymptotes, horizontal asymptotes, no. Intercepts, well, we know the function is 0, f of x equals 0 at x equals 6, and at x equals 0 the function is the cube root of minus 6. So those are our intercepts, and now we can deal with the first derivative. First derivative, we simply bring down the third and multiply by x minus 6, drop the power by 1, and then multiply by the derivative of the inside function, which is just 1. And whenever you have a negative exponent, it's useful to put it on the bottom of the fraction just to make it clear whether you're dealing with a 0 or you're dealing with a does not exist. When you do this, you can see that for x equals 6, f dashed of x does not exist. And in fact, because there is a power of 2 here in the numerator, it does not exist. It's a double event. Okay. Second derivative. Bring down the 2/3, we get negative 2 over 9. X minus 6, drop the power by 1, we get minus 5 over 3. Again, we'll write that as a fraction to keep it clear. We can put negative 2 on top, 9 on the bottom, x minus 6 to the positive 5 over 3. And therefore, for x equals 6, f double dashed of x does not exist. And we've got a power of 5, so it's times 5. So we don't have any zeros for f dashed of x or f double dashed of x, but we do have a couple of does not exists. So let's make our strip chart now and see what that all means. So we know that for the original function we have a 0 at x equals 6. And we know that for the derivative we have does not exist times 2, and for the second derivative we have the derivative does not exist times 5. Let's now look at the values of the slopes in those areas. So to the left of 6, f dashed of x, and we're looking at this expression here. So if x is less than 6, I'm going to get a very negative number here, but I'm going to square it and then take the cube root, so it's going to be a positive number. And so over here the slope is positive. For numbers greater than 6, x minus 6 will be positive, and obviously when I square it and take the cube root, that will also be positive. So the slope of the function remains positive throughout. And what's happening with the second derivative? Well, if I'm less than 6, this is a negative number. It's raised to the power of 5, so it stays negative. Take the cube root, so it stays negative. But it's multiplied by negative 2, so it ends up positive. And finally, if I'm greater than 6, well then x minus 6 will be a positive number, raised to the power of 5, taking the cube root, all positive, and then just the negative sign on top will cause the second derivative to be negative. So what do we have? We have a positive slope going to a positive slope, and we have a positive second derivative, which means curvature in this direction becoming curvature in this direction. Change in curvature implies that we have an inflection. Okay, now can we draw a graph of this with this information? So what do we need? We need a 0 at 6. That's clear from the function. We need an f dashed that is positive and also a curvature that's positive. Well, if I want to have a positive slope and be curving up, that means I'm looking at this kind of shape. So I'm going to be coming this away, coming in, and then going out I have a positive slope, but I have a negative curvature. A positive slope, negative curvature means this away. Those two together. So I'm coming out going this away. And what I have, as we've established, is an inflection point at x equals 6. Now as x tends to infinity, this thing is going to go off to positive infinity, and the cube root will head off towards negative infinity. And so that's it. That's the graph of this particular function. Okay, let's now look at example number 4. This will be our last example. It's a little more complicated than the others, but we follow the same procedure. Our function this time, f of x, is 10 x plus 1, and that's all divided by x minus 1 squared. So step number 1, we look at discontinuities. So discontinuities, we're looking for any kinds of breaks in the function, vertical asymptotes, horizontal asymptotes. What do we have? When x is equal to 1, we can see that the denominator becomes 0. So x equals 1 is a vertical asymptote. We can see that the degree of the polynomial is less on the top than on the bottom. So we know that y equals 0 is a horizontal asymptote. And we don't have any other discontinuities in the function. Next we look at intercepts. So f of 0 is 10 divided by -1 squared. So we know that a point on the graph is 0, 10. And when is f of x equal to 0? Well, that's when the numerator is 0, so we know that x must be -1. And so we have another point on the graph, -1, 0. Now we move on to the derivative part. So let's do f dashed of x first. Now here we use the quotient rule, which I hope everyone remembers. We bring the denominator up first of all, and we multiply by the derivative of the numerator, which in this case is just 10. We subtract from that the numerator multiplied by the derivative of the denominator. So we bring down the 2. That gives me x minus 1 to the power of 1, and then we multiply by the derivative inside the bracket, and that's just another 1. And finally we divide all of that by the square of the denominator, which takes us from x squared to x to the power of 4. Now we can simplify this expression. We've got a common factor of x minus 1, top and bottom. So we can divide each term by x minus 1. The first term reduces to this. Second term reduces to 10 into x plus 1 times 2. And that is all now divided by x minus 1, now to the power of 3, because we cancelled one x minus 1 term top and bottom. And if we gather up the like terms, we've got 10 lots of x here, minus 20 lots of x here, so that gives me negative 10x. Here I've got a negative 10. Here I've got negative 20. So that would be negative 30. All divided by x minus 1 cubed. So there's our f dashed of x. So now that we have the expression for the first derivative, we can work out the critical points. And those are when f dashed of x is 0 or does not exist. So when x equals 1, we can see that f dashed of x does not exist. So there's a critical point. And the other one is when x equals negative 3, f dashed of x is equal to 0. So there's another critical point. Next we do the second derivative. Again, we need to use the quotient rule. Now I'll let you work through that, but basically we're taking the derivative of this function over here. And using the quotient rule, you should be able to prove that f double dashed is equal to 20x plus 100 divided by x minus 1 to the power of 4. And so here we have critical points again. We can see that if x equals 1, the second derivative of x does not exist. So that's a critical point. And we can also see that if x equals negative 5, the second derivative is equal to 0. So that's another critical point. So let's make the strip chart first. So we have f of x, f dashed of x, and f double dashed of x. Now, what are the critical points we need to mark on this chart? So we know x equals 1 needs to be there, x equals negative 3, negative 5, and we also know that we have a 0 in the function at negative 1. Negative 5, negative 3, negative 1, and positive 1. So in terms of the function f, we know that we have a 0 at negative 1, so we mark that with a solid line. And we also know for the function that we have a vertical asymptote at x equals 1, so we'll show that as discontinuity in the function here. And in fact it's a squared term in the function, so we'll show it as a double discontinuity. Now f dashed of x, what have we got? We've got x equals 1, does not exist, and it is a cubed term, so we will show a triple discontinuity because of this exponent in the expression. We also know that at x equals minus 3, the derivative is 0, so we can put that as a solid line on the f dash strip. And finally, going to f double dashed, at x equals 1, the second derivative does not exist, and it's raised to a power of 4, so we will show it as a fourfold discontinuity. And at minus 5 we have a 0. And now let's look at the sign of the first derivative in each of these sections. So first of all, over here to the left of negative 3, let's look at the first derivative function. Let's put in a negative 4, for example. If we feed negative 4 into this expression over here, that will give us negative 4 times negative 10, so positive 40 on the top minus 30, so a positive number on top. And on the bottom we've got x minus 1 cubed, so a negative number cubed is negative. So we know that in this zone the slope is negative, so the function is heading in a downward direction. Once we cross the negative 3 boundary, we can put in any value above negative 3 and below positive 1. So let's put in a 0. If we put 0 into the f dashed formula, we'll get negative 30, over -1. So we get a positive value for the slope in this region. So the function is increasing in this region over here. And if we go beyond +1, we can see that our numerator becomes negative, our denominator becomes positive, and so our slope is again negative. Now if we look at the second derivative, again we can choose numbers to plug in to the left of -5. So if we plug in -6 into the second derivative formula, and -6 will give me a negative on top. The denominator is to a power of 4, so it will always be positive, and therefore I know that I am negative to the left of -5. Once we move to the right, we could put in a value of 0, and we can see we get 100 divided by a positive number. So this entire region here is positive. And then once we're above 1, we're going to get a positive number on top, positive on the bottom. So again, we're positive. So these second derivative numbers tell us the shape, the general shape of the curvature. So we've got negative curvature in this region, positive curvature in this region, and positive curvature in this region. And now we have everything we need to plot the graph, so let's plot it. Okay, so looking down all the information we have, we know that at x equals 1, the function has a vertical asymptote. So we can show that first of all. The next piece of information we have is that we have an intercept at -1, 0, and another intercept at 0 and 10. -3, we have the slope going from negative to positive, and so this point here meets the description of a minimum. So we have a minimum occurring down here. Nothing happening in between those two, so we know that our function is going this way towards the asymptote. Now, what's happening at -5? We have negative curvature turning into positive curvature. And that means we have the conditions for an inflection point. So at -5, our curvature has to change from the negative direction to the positive direction. So we're going to come up like this, and then we're going to turn at -5 and head this way towards the horizontal asymptote, which we know is y equals 0. So that's given us the graph to the left of the vertical asymptote, to the right of the vertical asymptote. We know we are going to be approaching horizontal asymptote, so either from this side or this side. We simply need to know, is the function positive or negative when we move beyond +1. So if we choose a number slightly above 1, what would happen to the function? If we're slightly above 1, the denominator would be a very small positive number, and the numerator would be positive. So we have a positive divided by a very small positive, so we're going to get a very large positive number. So this is the other half of this function, not this guy. And there you have it. That's the plot of this function meeting all of the requirements. I think you would agree that that would be difficult to do without using the first and second derivatives to help us pinpoint key parts of the graph. So that's it for this particular video. I hope these examples have been helpful and that you're now able to tackle any problem they throw at you. Don't forget to like and subscribe if you have found this video useful, and to click on the bell if you want notification of new videos as I post them. Thanks very much for joining. See you next time.